Okay, so we're going to be talking about how orbitals combine to make what we recognize as molecular orbitals. So a lot of this stuff, like I said before in this meeting, is a lot of organic chemistry 2 or beyond stuff, which is stuff that you don't really need to worry about now if you don't completely get it. It's totally fine. And so generally, when we're thinking about molecular orbitals, what we're seeing here, we're seeing sp2 orbitals combining. So being able to recognize sp2, p orbitals, s orbitals, and all that stuff is sort of important. S orbitals look like a big orb, which you've probably seen. Uh, do you mind just pressing check and then pulling up the explanation, because it should pull up
Yeah.
it should pull up all the molecular orbitals. So if we scroll down, so we can see here that, keep scrolling down. So we can see here that the one on the very left, on this picture with the three molecular orbitals, the ones on the left, the ones that are spheres, that is an s orbital, and the ones that look like an infinity sign, that is a p orbital. And notice something, how the same colored lobes, quote unquote, so you see how s has one lobe, it's just the sphere, and the p has two lobes, one on either side. When the two lobes interact, when they're the same thing, they can combine and make a bigger orbital. But when they don't, it's sort of like how magnets repel each other. You can see how it got a lot smaller, and the if you're looking at the picture that I am, where we have the s orbital and the p orbital combining, where they have opposite lobe types, they try to get sort of away from each other, and it looks kind of weird, right? And scroll down some more, please. Yeah,
Mhm.
somebody else is showing their screen because I can't choose the actual topics in ALEKS that I want to go over, because I haven't done anything, because I wanted to have a fresh slate, but whatever. Okay, so back to this. This is talking about how p orbitals will overlap if they're standing straight up instead of side by side. So again, if the same orbitals are next to each other, they're going to combine. And if different orbitals are next to each other, they're going to stay far apart as if they were magnets, right? Does that all make sense so far? Um, I'm just going to keep going. If you guys have any questions, mention in the chat, or you can just talk to me. Either one is fine. I'm reading the chat as we go. And then if you scroll down a little bit more, maybe it'll show some more stuff. Yeah, and so this is another example where the p orbitals are lying on their sides. When the like orbitals are next to each other, which is usually going to be what occurs, uh, and when you're thinking about organic chemistry, this is later, this is Orgo 2, don't worry about it too much right now, but just remember that when like orbitals are next to each other, they're going to want to combine and become one big orbital. When two unlike orbitals are beside each other, they're going to want to sort of repel each other and become they're going to stay their separate orbitals. So if we go to a practice question, just go ahead and click practice. Let me answer this quick question in the group me. Oh, never mind. Sorry, I thought somebody was trying to have some help getting in here. So if we're looking at this, it's sort of a, this is sort of a weird question, because we see we have an p orbital flat, but we also have another p orbital, and it's sort of, it is sort of going into the screen and out of the screen. If we scroll down, I don't really like I don't like this first question where it's like, if the orbitals can be combined, can it occur? Like, can this occur? I don't really like this, because it's sort of like stopping you before you go on. But let's just start with this already. So these two orbitals, they're not in line with each other. So they can't really form a molecular orbital because there are no nodes next to each other, right? So if you click no, then that should be the end of this question, right? You can't click anything else, right? Or yeah, so like I said right before, the nodes have to sort of line up. So if you have one that's on its side, like the one on the left, it has to be paired with another one that's on its side. If you have one that's into and out of the screen, like the one on the right, it has to have another one that's into or out of the screen, okay, if we have a p orbital. Okay, so the next question. Okay, so now what we have here, we have a p orbital, or this isn't quite a p orbital because it's like, it doesn't look like a p orbital, right? It doesn't look like a p orbital at all. That's because it's an sp orbital, and it's going to come together with another s orbital to make an sp2 orbital. So yes, it's going to come together and it's going to make sp2. Yeah, sorry. Just making sure I'm doing the math in my head right. And if we look down,
I can only click sigma or pi. So should
oh,
I?
then it's going to be sigma pi. It should
Okay.
be both of them. Yeah,
Okay.
because whenever you have a whenever you have an s orbital combining with a p orbital, you can't really make a double bond as easily as if you have two p orbitals coming together because of how the orbitals work. Again, this is an Orgo 2 thing that you guys don't really need to worry about it right now. Honestly, I hate this section in ALEKS, but whatever, everybody hates it. So if we scroll down, we know that we have two nodes that are next to each other, right? So they are going to combine. There's only one of these that combines them in the correct fashion that we've seen before when we're combining something that looks like P and something that looks like S. You guys don't have to say it, that's kind of awkward, but the bottom right one, if we click that one and we scroll back up to compare with what we were talking about earlier, you can see here that the s and the p orbital come together to make a big blob. And scroll back down real quick. I'm trying to figure out what they're looking for as far as the answer goes, what type of orbital is formed. I think you should just put pi,
Okay.
but I'm not exactly sure what it's totally asking. So press check real quick.
No.
Okay, what did we get wrong? Oh my god, I forgot ALEKS doesn't do that. Just do the explanation real quick. I don't know what we did wrong. Can you scroll down to the very bottom? Because that should have the answers, right? Okay, so sigma. So we put pi instead of sigma. The reason that it's sigma is usually when an S and a P come together, it is sigma. I just thought maybe it was pi because maybe it was trying to trick you, but no. So usually when we're looking at molecular orbitals, when they're on their side, like we see here in this example, it's usually going to be a sigma orbital or a molecular orbital, yeah. And then when you have, can you scroll up real quick? Right there. So when you see the lobes above and below the nodes, which are just the black dots, they're usually going to be pi orbitals. When they are consuming the dots, then it's going to be a sigma orbital. Okay? Does this all help clear up how molecular orbitals work and how to determine how to make them when given two orbitals? Okay. Let's do one more practice problem together, and then we can move on to something else if nobody has any more questions. So here we see two molecular orbitals. They're both p-ish, and so they're like nodes. They are in the same plane. They look like they're both on their side, so they line up. The two nodes, so yes, this can occur. And so now we don't say what type is formed yet because we have to figure out what our shape is before we can do that. So when we're looking at these two, so scroll back up to the actual picture. So we're looking at these two, we have two like nodes facing each other. So they are going to consume each other and become one big node together. So there's only one of these that does that. Yes, exactly, the top right one. And so if we look at this, they are a part of the node, part of the black dots, right? So it can't be a pi bond because they aren't above and below. So it has to be a sigma bond. Does this help with figuring out the molecular orbital stuff? At least I hope it does. I don't know why they have you as multiple answers on that question, because it just says to do the best ones. Did it not go through? Yep. See, so that should help clear up a lot of the questions that you have with molecular orbitals, right? Again,
So I have a question.
go ahead.
So a sigma bond basically means when the nodes are in like a straight line, and if they're like
Yes,
away from each
they're
other, that would be pi.
yes, because of the way that a pi bond works. I'm gonna go ahead and share my screen real quick so I can draw this out for you guys. This will stop the other screen share, so just give me 1 second to draw this out. So I have this set up already. So if we look at something like, let's ignore the periodic table that I have there real quick. Let's say we're looking at something that's C bonded to an H versus a C double bonded to another C. So when we look at a C bonded to an H, if we look at the actual electrons, it looks like this. And if we look at a C double bonded to another C, it looks like this. When we're looking at C bonded to an H, we can see that these electrons are of like charges, so they're going to push each other away as far as possible. So we're going to look at something sort of like this, right? With one of the nodes colored in, but we're not going to worry about that right now, okay? So we're pushing the electrons as far away as possible from one another. If we look at the C double bonded C, which is a pi bond, because when we have a double bond, that's comprised of a sigma bond and a pi bond. And a single bond is just a sigma bond, okay? When we look at a C double bond to a C, those electrons are going to want to push as far away as possible from each other. So they're going to look sort of like this, right? Wherever the nodes are, it doesn't really matter. Because it could look like this, or if the nodes match, it could look like this. Okay? But do you notice here how when they're trying to be as far apart as possible, they are not a part of that central dot when they include the when we have that double bond, which includes the pi bond, right? But when we have the single bond, which is just a sigma bond, they're going to be pushing away as far as possible. As far as possible just means to be in line with this dot. Does that make sense? Does that help with your question?
Yeah, it does.
Okay. So can you go back to sharing your screen?
Yeah.
Okay. All right, good. So I think that should answer everyone's question about molecular orbitals and how they combine together. Again, if you have any any more questions about it, then you can just direct message me on either GroupMe or through web courses. Either one is fine. I prefer if you message me through GroupMe because if you do that, then I can forward that information to everybody else in the same GroupMe. Okay, so that's it for molecular orbitals. I think I went over everything. Do we have any specific topics that people want to go over next? Or if not, then I'm just going to go into the organic chemistry stuff, which is sort of representations of organic molecules, which is what we're doing now, but we're going to do more of the other hard sections, okay? Okay, so can you click that arrow that pulls down all of the topics? Yeah, that one. So just scroll over a little bit. Let's do determining the product of curved arrows drawn in a skeletal structure, just because this is a really important thing when we're talking about mechanisms, which we're going to get into later. So when we're looking at something like this, what the arrows are doing is they show the movement of electrons. In organic chemistry, arrows are always going to show the movement of electrons and not the movement of individual atoms. Okay, let me steal this real quick, and then I'm going to go ahead and go back to sharing my screen just so I can draw this out for you guys. So let's go back here, back to this this screen here. So I have this here. Oh, I was gonna move that. Let me move it. Okay, it's not gonna let me move it, so I'm just gonna erase stuff. Okay, so again, I'm just gonna reiterate. When we're looking at arrows, we're looking at the movement of electrons. And arrows will always either come from a lone pair or a double bond, because both of those have extra electrons that they can give. Remember that a double bond, when we're just drawing the electrons, looks like two lone pairs on top of each other. So that means that they have an extra lone pair that they don't need to make that bond, okay? But when we're thinking about the movement of electrons in resonance structures, which would be what we're looking at here, we cannot draw arrows from a single bond because that would break the bond, okay? We will draw arrows from single bonds later in the class when we're talking about nucleophilic attack and stuff, but don't worry about that with ALEKS. I don't think that they're going to ask you to draw a mechanism before you know what a mechanism is, okay? And so one more thing to note is that you notice how these arrows are double-headed arrows. Double-headed arrows mean the movement of a full pair of electrons, okay? Single-headed arrows mean the movement of a single electron, okay? So if I drew something like, I don't know, Cl with like a bunch of extra electrons, this would be Cl negative, and then we had, I don't know, lithium plus, and I drew a double-headed arrow, then I would have a full Cl-Li bond because a full pair of electrons moved. However, if I just drew a single arrow, or single-headed arrow, if it looked like this, then only one of those electrons would move, and we would end up with two radicals. Radicals are essentially atoms with a oddly numbered amount of electrons, and they don't really have an actual charge because we don't really deal with half charges, okay? That's something important to remember about how arrows work, because this is going to be really important later. Now, if we look at this stuff, what I'm going to go ahead and do, I'm going to label all of these carbons, whether they're sp2, sp3, all of that stuff, okay? So if we look at this carbon, we know, even though it's not shown, that it's bonded to 3 other hydrogens. How do we know this? Well, we know that this carbon does not have a formal charge. That means that it has to be happy. All of its bonds have to be filled, okay? For a carbon to have a formal charge of 0, it has to have 4 bonds, not 4 electron groups, 4 bonds, okay? And when we're drawing the skeletal structure, then we assume that if we have a formal charge of 0 or a formal charge of whatever, that formal charge is going to be filled in with hidden hydrogens, okay? So here we have a carbon with 4 bonds. That means it's going to be sp3. Now, the way that I like to remember sp3 is that the amount of numbers that you have is the amount of electron groups that you have. So that might be confusing, but let's look at sp, sp2, sp3. So we have, for sp, we have 1 s and 1 p. That equals a total of 2. For sp2, we have 1 s and 2 p. That equals a total of 3. For sp3, we have 1 s and 3 p, a total of 4. So if we're looking at something like sp, that means the carbon has to have 2 electron groups around that. Usually what that means is a C triple bonded to something else, whether it be like a C or an N or whatever. It just has a triple bond and then a single bond to something else. So it has 2 electron groups attached to it. 2 corresponds with sp. Now, if we're looking at sp2, usually it's going to be a C double bonded to something and then single bond, single bond. It has 3 electron groups, so it has a total of 3, which corresponds with sp2. sp3, I'm going to do this, usually corresponds with just a carbon having 4 single bonds around it. 4 corresponds with 4, which corresponds with sp3. That's how I always remembered it. If you guys have a better way, then by all means do it. I just wanted to share that with you guys. Okay? So here we know this guy has 4 bonds, so it has to be sp3. Here, this carbon here has 1, 2, 3, 4 bonds already, so it does not need any of that hidden H's. And if we count around, we see it has 1, 2, 3 electron groups around it, so that means it's sp2. Okay? And then if we're looking at this one, it's the same deal, except this one does have a hidden H, so it has 1, 2, 3, and then needs one more bond to be happy. So it has 3 electron groups around it. It's going to be sp2, and so on. Okay, does that make sense? I'm going to assume it does unless anybody asks a question, but if not, that's totally fine. Okay, so when we're looking at the movements of electrons and stuff, we always have to try and make sure that the octet is upheld. Like it's always going to have 8 electrons around it. It can't have more, it can't have less. That's what it's asking when it says, is this a valid way to move electrons? Okay, so let's just erase all of this, and then we will draw out what happens when we use the arrows that they give us. Okay. So let's see what happens when we use the arrow that they give us. I'm just going to draw the general structure real quick without any extra bonds anywhere. Okay. So no double bonds anywhere. I'm just drawing the relative structure. So let's start with the nitrogen, okay? So we see we go from a lone pair into a bond. What that arrow means is the lone pair is making up a new pi bond, which means that we're going to now have a double bond here, okay? And then this arrow, it's going from a bond to another bond. That means that the double bond is just moving from one bond to another. So right there. And here we see we have a bond going to an atom. What that means is that a bond from that double bond is going to become a lone pair on that atom. Okay, so now we just draw out what we have. And whenever you see something that is that doesn't have any electrons around it, but it does have a formal charge of 0, it's assumed that it has the electrons around it that would make its formal charge 0. Okay? So let's check and make sure that the octet rule is filled and okay for every single one of these. This nitrogen, it has 2, 4, 6, 8. That's good. We have this carbon has 2, 4, 6. We think it's missing one, but then we remember there's a hidden hydrogen right there, 8. So that one's good. Oops. That's fine. And then here, we look at this carbon, has 2, 4, 6, 8. We're good. This oxygen has 8, 2, 4, 6, 8. And this carbon didn't change, so we can just assume that it's okay. Okay? So this structure is possible, but we're not done drawing it. I just wanted to make sure that it was possible before we moved on. Okay? So we have all the bonds drawn. We know that this is possible. The only thing that we're missing is the formal charges. Okay? And one more thing to note about when we're going between one resonant structure to another, because that's basically what this is. We're going from one compound to another compound where they both have the same general structure. It's just the double bonds and lone pairs move. That's a resonant structure. So what we have to do is we have to make sure that the net charge, which is the charge of the overall molecule, is the same on both of these. This is where the formal charge comes in. So if we look here, this one has a net charge of 0. So we have to make sure that this also has a net charge of 0. Okay? When we look at nitrogen, how many valence electrons does nitrogen have? So we'll go back up to our periodic table, and what I like to do, I like to count backwards, or start from this side and count up to see how many valence electrons it should have. So this one's 0, and then 1, 2, 3, 4, 5, etc. But these are basically the ones that we're going to be worried about. Okay? So if we look at nitrogen, that's right here, we know it has 3. So we start with 3, right? Oh no, I totally did it the wrong way. I'm so sorry. You start from 7 and you go 7, 6, 5, 4. Sorry, I was thinking about how many electrons or how many spaces are available for new electrons. Sorry, guys. But again, these are still 0. Okay? So let's go back. Nitrogen has 5. You're right. I'm so sorry. So nitrogen usually has 5. And then we see here we have 1, 2, 3, 4 bonds and 0 lone pairs. So 5 minus 4 minus 0, that equals +1. So that means that this nitrogen has a formal charge of +1. Okay? So that means that we have to have a -1 somewhere. All of these carbons look okay because they have 4 bonds, which makes sense because the formal charge of carbon, for it to be 0, it has to have 4 bonds because 4 minus 4 is 0. So that's totally fine. So the only other atom that's different from carbon and hydrogens is this oxygen. We call this, whatever atom that's not carbon and hydrogen, we call those heteroatoms. So the nitrogen and the oxygen, those are heteroatoms. So we're focusing on the heteroatoms here. If we look at oxygen, how many valence electrons does oxygen have? And if we want to look back up at our table, it's 6, obviously. So we go from 0, 7, 6, 5, 4. Okay? We don't really go past this because we don't deal with stuff like boron, aluminum, gallium, stuff like that, except in special cases. Boron is used in special cases, but you'll see that later down the line when we talk about reduction and oxidation reactions, okay? Okay, so oxygen has 6. And so we can see here it has 1 bond. Oh, it has 1 bond, and then 1, 2, 3 lone pairs, which means it has 6 electrons in lone pairs. So that means that its formal charge is -1. So we have a formal charge here of -1, which means that this +1, this -1, they both cancel out and we get 0. So that means that yes, this is valid because it has all of the atoms in it follow the octet rule, which means they have 8 electrons. And then the formal charge or the net charge are the same for both of these. So that means that yes, this is a possible structure. So this is valid, okay? I just walked you through all of that stuff. I don't think I need to do too many more examples, but if we want to do one more, could you share your screen one more time? All right, perfect. And so if you want to just type out, so what it means by a reasonable structure is what I just said before. So either just do the answer or just do like the explanation so we can go on to another example.
Yeah, I'll just do explanation.
Yeah. We'll just go on to the next one. Okay, good. So when we're looking at this right here, I'm gonna share my screen one more time. Hold on, let me take a screenshot of this real quick. And then I'm gonna walk you through this one more time, and then we're gonna move on to the next concept, if that's okay with everybody. Just shout out if you want to do this some more, if you want to do something else. I don't mind either way. Okay. Let me just share my screen. Okay, so let's follow these arrows. So this arrow right here, it's going from one bond to another bond, which means that you're just going to be making another double bond. This one's going from a double bond to an atom, which means we're going to be putting an electron right there, okay? Okay, and I'm going to be marking out what kind of carbons that we have again. So this is sp2, this is sp3, this is sp2, okay? And usually the hybridization of carbons are going to stay the same between two different resonance structures. So let's draw this resonance structure. So I'm going to start by just drawing out the basic structure. No charges, no extra bonds or anything. Okay. So let's go back to this. We see that we move from this double bond to make a double bond right there. So I draw that in. We see we go from a double bond here to electrons being on this nitrogen. So we draw that there. Okay, so now we make sure everything follows the octet rule. Again, like I said before, it's implied that if it's not shown that there are electrons there that make that formal charge into 0. So this guy is still gonna still have these lone pairs here. Okay. So let's count up this octet rule. But I see one problem already. If this carbon here was sp2 before, that means it only has one hydrogen, which means that this carbon here still only has one hydrogen, which means that it only has 6 electrons around it. This is okay because we're not invalidating the octet rule because we're not going above 8. If we go above 8, that would invalidate the octet rule. If we go below, that's okay as long as the net charge stays the same. Okay? So I'm going to go ahead and tell you right here that both of these nitrogens have a net charge of 0, or a formal charge of 0. And the only other thing that changed was this carbon. So I'd see the formal charge for that carbon. C has 4 valence electrons. It has 3 bonds, no lone pairs. So it has a charge of +1. So that means that this carbon here now has a plus charge. And we can note that the +1 was retained between the 2 structures. So yes, this is valid. Okay? Does that make sense? If not, that's fine. Just let me know. Let me check. Okay, so everybody's good. Okay, so go ahead and go back to sharing your own screen, and then we'll go on to the next topic. I think I covered the hardest one, which was the molecular orbital stuff, but it's all good. Okay. So that topic is really important for organic chemistry when it comes to the movement of electrons because of mechanisms. Okay, so let's do interpreting a flipped or rotated dash wedge skeletal structure. This will help you with, okay, so this will definitely help you with something called stereochemistry that will come on later that a lot of people have issue with, okay? So stereochemistry is basically how the molecule looks in space, if something is in front of you, if something's behind you, and all that stuff. When you have a solid wedge, that means that the whatever is on that wedge is pointing out of the screen towards you. Whenever you have a dashed wedge, that means whatever is on that dashed wedge is pointing into the screen away from you, okay? It's like if I like to show it by doing a peace sign with my fingers and just rotating it. And the finger that's towards me would be a solid wedge, and the finger that's away from me would be a dashed wedge, okay? So when we're looking at something rotating 180 degrees, we're looking to see if those, okay. So when you're looking at your hands, I know this seems like sort of a weird thing to do, but if you're looking at your hands, because I'm using what they have here, your hands are mirror images of each other. However, you cannot rotate your hands so that they perfectly align with one another, okay? So if you just try rotating your hands without flipping them, you can't align them. That's something important to keep in mind for chiral or achiral molecules. I'm getting into stuff that I think is a little bit advanced, but it's important to note for this type of problem. When I think of rotating, I think of, okay, so if I held one molecule in the same place and I just rotated it about that molecule, would it be the same? Okay? So if we look at this first one, yes. Let's say we rotated it about that center one, okay? And what we do, we just kind of rotate it over and the oxygen is on the left and the OHH is on the right. Nothing else changed, okay? This is important because it's not the mirror image. The mirror image would have the OH and H on the other side, okay? Does that make sense? Another way you can rotate it is you can rotate it into the screen or out of the screen. I don't know if they have an example here. I don't think so. Like if you look at the second one, so if we look at the second one in the top row, this would be a mirror image. Okay, so this is sort of hard to understand, but it's a mirror image if you took a mirror and held it up to your screen straight on. Okay? So the OH is now into the screen and the H is now out of the screen because it's as if you took a mirror to that towards the screen and just flip-flop those. That is not a rotation, that is a reflection. Okay? The next one is also a little tricky because you're it's also a reflection, but it's not a reflection, sorry. I totally blanked there for a second. It's not a reflection. I can tell you this because of my knowledge of organic chemistry, but if we just look at it from a rotational standpoint, it's as if you took that image on the example and you wrote it as if it were a mirror image to the left. Okay? And then you did it, but then what you did is you rotated it again. So, okay. So I'm really sorry. This is really hard for people who don't have a good sense of three-dimensional space. I don't have the greatest sense of three-dimensional space. So usually what I do is I use something called S&R configurations, which is something that you'll learn later. And all of this will become way easier. Okay? I promise it'll become way easier because I know for sure that I'm not great with spatial recognition. So I always use like my cheat sheet with different configurations. So here you if you do have the molecular kit, that will definitely help with this. If you don't, what I would do is I would go online, go to, I think it's called MOLVIEW. I'll write it down. It's MolView. And that will definitely help you rotate that molecule around and figure out if these are right. Does that all make sense? Like basically what you have to do is you have to have either a good sense of three-dimensional structure in your head or kind of cheese it and use something in your house, either a molecular kit or MolView. Okay? So scroll back up to it real quick. Yeah, so this is just something that you have to sort of either understand in your head or use like little cheats like I do, which I will definitely explain later. Um it's just a little bit advanced to be talking about right now, and I don't want to confuse you because you have a lot of information going through your head. I just say use MolView or use a molecular kit that you got. Okay? Does that work for everybody? I'm sorry I couldn't help so much with this. It's just because I have not the greatest sense of three-dimensional structure, and I always use a different type of method that I can't teach you right now, but I will teach you later. Okay? And if you have any questions about it, I can definitely help you using MolView. DM me or message me on web courses. It's whatever. Okay? Okay, so let's go on to the next topic. So move over to the did we do recognizing typical LCAO? Oh, you can't do that one yet because it's locked, huh? Okay, just keep going to the right. If somebody else has that unlocked, we can work with it. Does that make sense? So did we do understanding the 3D shape of no, we didn't. Let's do the interpreting skeletal structures at the very end. Yeah. So skeletal resonance structures, it's something that we have done before in some of these questions. So we have to figure out, oh, is this a valid resonance structure? Okay, so what I'm going to do is I'm going to do what I did before, and I'm going to snip this, just take a screenshot of it and draw it on it using my my OneNote. Okay, okay, okay. Okay. Let me just make a new page for this. Yeah, that'll be easier. So when we're looking at resonance structure and to see whether or not these resonance structures are valid, is we're sort of wanting to see if any bonds moved other than pi bonds or lone pairs. So I'm going to go ahead and draw in all of the other parts to these skeletal structures. Essentially what I'm going to do is I'm going to draw in all of the hydrogens that we can't see. So there's a hydrogen right here, a hydrogen right here, 3 hydrogens right here, and then this guy here says it has a positive charge. That means if we do our formal charge, C equals 4 minus X, our variable, equals plus 1, that means, or plus 1, that means that X has to equal 3. So that means that the carbon can only have 3 bonds, which is what we see right here. 1, 2, 3. Okay? And then I'm going to go ahead and draw in the lone pairs for this oxygen. All right. And so now I'm going to draw in, I'm going to do the same thing with this one right here. 3 hydrogens, hydrogen, 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 2 hydrogens, no hydrogens. And then if this is positively charged, it's going to have to be 6 minus, because we're trying to figure out the number of lone electrons. It's going to be 6 minus 3 minus X equals plus 1. 6 minus 3 is 3. X equals 2. 2. Yeah, 2. So that means, yes, there's only 1 pair of electrons here. That means we aren't violating the octet rule in any way, so both of these structures are valid and can exist. Now what we need to do is determine if the resonance structure is valid. So what we're going to do here is we're going to ignore everything that does not change. So we're just going to ignore all of this stuff. We're just going to be focusing on this carbon, or this carbon as well, and then this oxygen. Okay? Okay. So what we see here is we go from 2 lone pairs and 1 double bond to 1 triple bond and 1 lone pair. What this means is we're going from 1 sigma bond and 1 pi bond to 1 sigma bond and 2 pi bonds. And pi bonds are made of lone pairs. So if we have 1 pi bond here, that means we only have 1 lone pair. If we have 2 pi bonds, and we have 4 lone pairs participating. Okay? So that means that here's a lone pair on this bond here, here's a lone pair on this bond here. Now, to determine if this is valid, we have to figure out where this lone pair came from. And we can see over here that we go from 2 lone pairs on this oxygen to 1 lone pair on this oxygen. So this is where the lone pair came from. This is a valid resonance structure. And the way that we would draw this is the lone pair from this oxygen is going to go onto this double bond and make a triple bond right here. Okay? And the reason that the positive charge changes is because this carbon here gets 4 bonds. This triple bond, so that's going to be 3, and then this single bond, which is going to be 1. So it has 4 bonds, it's happy. Over here, it had 3 bonds, so it has a positive charge, it's not as happy. But then that positive charge moves onto the oxygen. Okay? So what that means is, yes, this is a valid resonance structure. Okay? Okay. Now let's go on to this next one. I'm not gonna draw in the extra stuff for these two because they just don't participate in the reaction at all. So I'm just gonna mark it out real quick. Okay. So we know that this carbon has a negative charge. Okay. We know that carbon can't have more than 8 electrons. It has to equal 8. Same here. All that stuff. So that means that the total amount of electrons has to equal 8. And if we have a negative formal charge, so we have 4 minus 2. I'm trying to do this mathematically in your head, but if I know what the answer is. It's just going to have a lone pair on this carbon here with an H here. And if we do the math, we have 4 minus 3 minus 2 that equals -1. That lines up with this. Okay? So I'm going to get rid of that hydrogen, and I'm just going to draw the lone pair because it'll make things less cluttered. Okay? And the same thing occurs over here, where this has the lone pair. Okay? This is a little bit trickier, and I'm gonna go ahead and tell you the answer. No, it can't be a resonance structure because if we look over here, this hydrogen or this carbon is happy, so it has the 3 hydrogen at once. Over here, this carbon is happy, so it has the 2 hydrogen at once. Okay? That means that to become this guy over here, one of the hydrogens from this had to move all the way over here, which is not possible if we're talking about resonance structures. So no, it cannot be a resonance structure. Okay? Does that all make sense so far? I'm gonna hope yes, and I'm gonna go ahead and stop sharing my screen, or can you start sharing your screen one more time? I'm trying to go over the organic chemistry stuff that's going to help you the most in the class, or the stuff that's going to be the hardest, okay? So can you bring down the lessons again? Sorry. Yeah. Okay, so yeah, we'll just do this one, and this will be the last one because we've almost been going for an hour, and my throat's kind of hurting. Okay, so examine the highlighted bond on the structure below. Select all the pictures in the table that correctly show the 3-dimensional arrangements on both sides of the highlighted bond. Okay, so I'm gonna screen cap that again. Let me just grab this. Okay. And then I'm gonna start sharing my screen again in 1 second. Let me just move this over here. Okay. Okay. Share screen. Oh, that's not the right one. That's just my snipping tool. There we go. Okay. So if we're looking at something like this, what we have to do is we have to determine the spatial configuration of something like this. So when we're talking about stuff like sp3, sp2, sp, there are specific geometries associated with them. So sp3, as far as carbon goes, sp3 equals tetrahedral. I'm just going to write tetra. sp2 equals trigonal planar. I'm just going to write trig. sp equals linear. Okay? This is because, so let's say we had a carbon here and it had 4 bonds, which would make it sp3. We would have 1 up, 1 to the front, 1 to the back, and then 1 to the side, where it kind of looks like a pyramid with something coming out of it. That means it's tetrahedral. If we had, again, these molecular geometries have to do with the position of electrons and them wanting to get as far apart as possible. And so the next one is trigonal planar. Again, this means that you only have 3 bonds. It could be, any one of these could be the double bond. Like this one could be the double bond, this could be the double bond. It doesn't matter, just as long as it's trigonal planar. So what trigonal planar means is that they're all in the same plane. They're all just a regular triangle. No three dimensions to worry about. So with tetrahedral, you do worry about 3 dimensions because it looks like this. Okay? With trigonal planar, it's 2D, but you can worry about 3D in the way that you can have the triangle right in the plane, you can have the triangle going into the plane, you can have the triangle going out of the plane. This is something that we'll discuss in a second. Okay? Linear, that's pretty self-explanatory. It's just going to be a line. And if we're thinking about 3D, it's either going to be a line just right there, up or down, into the page. It's whatever. But right now, what we're going to be worried about is this bond right here. Now, I'm going to go ahead and draw on the other bonds. So we have an H here, an H here, and an H here. Okay? And these 2 carbons, which are the 2 carbons that we're worrying about, they're both sp2. That means they're both trigonal planar. So that means if we drew this out 3-dimensionally and we just wanted to draw it out into the plane, it would just be straight out onto the plane, H, H. This would be the CH3 group, it doesn't matter. This is CH3, and then H. So this is what it looks like. You don't need any 3 dimensions on it. However, if it does ask for 3 dimensions, it's kind of like turning a piece of paper on its side. So remember how I said that solid wedges are coming out and dashed wedges are going in? If we turn this so the 2 H's are in the front, it would look like this, where there are 2 H's on the dashes, or I mean the solid wedges. And there'd be a CH3 on the dashed and another H on the dash, okay? And if we turn it the other way so that these were in the front, it would look like this. Okay, does that help with 3-dimensionality and stuff? Like the trigonal planar is the one you have to worry about the most with 3-dimensional structures. I mean the tetrahedral one is the one you have to worry about the most. The trigonal planar is a little bit easier because it's sort of just like rotating a piece of paper because it is planar. Okay? Okay, can you pull up your screen one more time? I want to look at the next one if we can. The next question, and then we'll call it for the day. Okay. So this is basically the same thing. It's just one more thing that's important to notice is I'm gonna snip this one more time. Uh, yep, and do my share screen thing again. Yes. Okay. So the one thing that's really important to note about this guy is that you have not all H's in one. You have 2 CH3s that are pointing in opposite directions. One's pointing up and one's pointing down. This is referred to as trans, or something else that's a little bit too much for right now. But all you have to remember is that they're on opposite sides. So if I'm going to draw the rest of the H's. H. So if I just drew this straight like I did before, I would have to make sure one of the CH3s is up and one of the CH3s is down, and then you have H and H. Now, if we rotated this so that this side was in the front, it would look like this. CH3, H, CH3 in the back, H in the back. Okay? Does that make sense? It's just important to note where the stuff is on these. Like, let's say we had something like this. This is called cis. Don't worry about that right now. If we drew this, sorry, let me draw this a little bit better. That's not very much better. But if we drew this like we did before, we'd have CH3 on this side, CH3 on this side, H on this side, H on this side. So now the CH3 is on the same side. So if we rotated it again, we'd have CH3 in the front, CH3 in the front, and then H is in the back, and vice versa. Okay, so that's just something to keep in mind when we're thinking about 3-dimensional structures. I think that's it for today. There is a question in Oh, okay. So let's talk about acids and bases real quick. I'm just gonna make a new section for this. Acids in Bronsted-Lowry acid. So I'm gonna put BL acids, or BL versus Lewis. Okay, this is pretty easy. Honestly, it's not that hard. It just seems a lot harder than it is. So Bronsted-Lowry acid, they donate hydrogens. Okay. Lewis acids, they accept electrons. Okay. Bronsted-Lowry bases accept, that should be a C, accept hydrogens. And then Lewis bases donate electrons. So let's see this happening. So I will have HA plus B. Oop. We're going to be talking about Bronsted-Lowry with this one, okay? So we see that this acid has an H, and this base, it will either be neutrally charged or negatively charged. I'm just going to make it negatively charged so it's a little bit easier. So what happens is that we have an electron pair from this base grabs the hydrogen, and then we get a negative plus HB. Okay? Now let's say we had just A plus B over here. This B would be negative again, and this A would probably be positive or neutral. I'm just gonna make it positive for ease of understanding. So what happens here is the same thing. The B electrons are going to be donated to this acid. And so then we have A neutral plus B neutral, okay? So notice something here. We had a neutrally charged acid in the Bronsted-Lowry. It became negatively charged. So it lost a charge, so -1. The base, it went from negatively charged to neutrally charged. So it gained a charge, so +1. If we look here, the same thing happened. This one went from negative to neutral, so it gained 1 charge. This one went from positive to neutral, so it lost 1 charge. What's important to note are the base similarity between Bronsted-Lowry acids and Lewis acids and bases and stuff like that is the idea that the acid is usually going to be positive or neutral, and the base is usually going to be negative or neutral, okay? And when we're trying to determine a strong acid versus a strong base, let's say we had, we're going to be using the Bronsted-Lowry definition from now on in this class. The Lewis and Bronsted-Lowry, it's just important to differentiate between the two. So now let's talk about strong Bronsted-Lowry acids and strong Bronsted-Lowry bases. So again, we have H, A, and B. What makes something strong? What makes an acid strong? What makes a base strong? Well, what makes an acid strong is how well it donates that hydrogen. And what makes a base strong is how well it accepts that hydrogen. So -H plus H. Okay? So when we lose an hydrogen with the acid, we're left with a negative. And when we gain that that hydrogen for base, we either end up with HB plus or HB. I'm just going to make it HB for now because we're just going to focus on acids first. So when we're looking at acids, the more stable the acid is on its own without the hydrogen, the stronger the acid is going to be. So if we look at something like HCl versus HC, Cl negative is more stable than C negative when both of these lose an H. Okay, so that means that HCl is going to be the stronger acid. Okay. On the flip side, when we're looking at a base, the less stable a base is without that hydrogen, the more desperate it is to get a hydrogen to fill that spot, the stronger it is. So the less stable a base, the stronger it is. So again, if we had C negative versus Cl negative, C negative is a stronger base because it's less stable. Okay? So what makes an acid strong? Just to review. The more stable the acid is without that H, the stronger it is. And the less stable that a base is without that H, the stronger it is. Okay? So if we had, let's say we had HCl plus Cl, just C negative. I don't know. I'm going to put CH2, CH3 negative because that's what I'm used to, but it doesn't matter. And we had something at equilibrium. These are equilibrium arrows. You've probably seen them before. And we had Cl negative plus CH4. When we're looking at acid-base reactions, the reaction is always going to proceed towards the weaker acid-base pair. So whichever one has the strong acid or the strong base on that side, it's going to go to the opposite. So we've established before that HCl is a stronger acid than this. And we've established again that CH3 is a stronger base than HCl. So when we're comparing the two acids, so when we're comparing something, if we're trying to figure out which end it's going to go to, what I usually do is I compare the two possible acids. Usually the acids are going to be positively charged or neutrally charged, so we can sort of just ignore these two. So let's look at HCl versus CH4. If they lost their H's and we had Cl negative versus CH3 negative, which one's more stable? That's a rhetorical question. It's Cl. Cl is more stable, so that means that HCl is the stronger acid. So this whole thing is going to go towards the right, towards the weaker acid, towards the weaker base. If we did this again when comparing the bases instead, if we compared CH3 negative versus Cl negative, again, we know that CH3 negative is less stable. So that means that this is the stronger base. It's going to go towards the weaker base. It's going to go towards the right. Okay? Okay, so we've been going for a good hour now. I'm going to go ahead and stop. Again, if you have any additional questions, just let me know. And I will see you next time. I'm going to go ahead and stop the recording. How do I do that?